Could a black hole be thought of as its own kind of fundamental particle? Yes. Incredibly, it might not be that inaccurate to say that a black hole is a special kind of fundamental particle. When we think about the fundamental particles of the standard model of particle physics, like electrons and muons and other fundamental particles, these objects often behave like point particles. They don't have a finite extent. They're like infinitesimally small. It's only when these fundamental particles interact with other objects, other types of fundamental particles, that they get a finite volume, like when an electron interacts with the nucleus of an atom to make the volume of like a hydrogen atom. And you might be thinking, well, what about a neutron and a proton? Those have like a radius that's been measured. Well, those are not fundamental particles. The neutron and the proton are actually composed out of quarks and gluons. And quarks and gluons have never been observed go freely about for other reasons, but not only that, but not limited to just the fact that the nature of the gluons is very different than, like, say, the force that describes the electromagnetic force of the electron. The gluon force is the strong force. It's very hard to pull these things apart. Some would say it's infinitely hard. It's still a little bit of a debate, but again, this point-like nature might be one of the reasons for that difficulty. So gluons might behave like point particles too. We don't really know. But the whole point of this is that the black hole is a singular point in space and time. And it's incredible to think that something as complex and different as a black hole might be analogous to an electron or something like that in a weird way, that it has the same spatial extent of being a point. So you could almost think of a black hole as a type of fundamental particle, but you won't see it listed in the standard model of particle physics. Well, why is that? Well, there's a number of reasons. First of all, you can't create a black hole with any other theory of science other than general relativity. And the standard model of particle physics is not compatible with general relativity. So right now, black holes are a general relativistic object outside of the domain of the standard model of particle physics. So that's one reason why you won't hear a black hole called a fundamental particle. But it's interesting to think about. Star mergers happen when two stars get close together and they actually merge into one giant star. This is a very dynamical event, and it depends on the masses of the stars involved and how things go. For example, if we have one type of star is a neutron star and the other star is, say, a red dwarf, the neutron star can actually steal the outer elements of the red giant and actually form a black hole by gaining enough mass to overcome the neutron degeneracy pressure and then form into a black hole. It's a very fascinating process. It's very difficult to show this with Barnes-Hut simulations that I usually use, so I'll probably not make a simulation of that, but I am going to make simulations of other types of star mergers. Another type is where you have one very compact star and another with a more bigger atmosphere. Stars have very large atmospheres in some cases, and the atmosphere can get pulled off by the smaller star and become part of the other star system before the two stars merge into one. When this merger happens, they could again form into a black hole possibly, or they could form into some other kind of object. If it's not enough mass, it could form into a neutron star, or it could form into a white dwarf if the two stars were originally very low mass. So here we have a large star with an atmosphere and a more densely held star. Now, when these two merge, the atmospheric components go on the outside. And in actuality, some of that would actually get pulled into the core immediately. But you get the general idea. We have that this forms into one giant star with a more prominent atmosphere. We can also have it that a star actually steals from a gas cloud. So here we have a small cloud of gas that's getting pulled under the gravitational influence of a star. And in actuality, when these mass components of gas get close enough, this system would just capture it. However, this simulation only models gravitational influences. So you'll have to use your imagination a little bit. I do work with high resolution simulations called fire simulations, which actually do have the dynamical processes where when the gas gets close enough to the star, it merges and becomes part of the star itself, and the star actually gains mass. But these Barnes Hut simulations are just a lot simpler, but they're still nice to see. You can see how this gas cloud has been completely engulfed by the star, and in reality, all these gas points would not be hovering, they would just be emerged. Get ready, because tomorrow we're returning to the moon. That's right, Artemis 1 is launching tomorrow. Now, this mission is a very complex operation. It is unmanned, and nobody's actually going to set foot on the moon, but the ship is going to blast off from Earth and enter a retrograde orbit around the moon and release satellites, which are important tools that will assist us in future missions where we actually set foot on the moon. So this is a first step in reaching what will come to be an age where we actually set foot on the moon more regularly. We need more equipment and satellites to assist in GPS around the moon, just like we have these GPS satellites that assist us with locations and communications around Earth. So, while it's unmanned, this is a very big deal, and it's a very fascinating mission because the orbit that the ship is going to actually enter is a retrograde orbit at a Lagrange point. And if you've studied classical mechanics, you know a Lagrange point is a mathematical solution to the three-body problem. What do I mean by three-body problem? Well, we have three gravitating bodies, the Earth, the Moon, and the much smaller massed spaceship. Now, at this Lagrange point, there's an equilibrium point where the gravitational pull from the Earth and the Moon is equal, and this is a stability point, which is very useful because it's a lot easier to maneuver at this specific location. The calculations are a lot simpler for the crew on Earth that's actually guiding this ship. So that's why they've chosen this location. Now, this mission is going to last about 3 weeks, and then the ship is actually going to return to Earth and splash down. This reason that it's going to actually return to Earth is twofold. Number one, it saves us money because we don't lose a ship and have to worry about maybe it being destroyed. Now, I'm not 100% certain that the ship will be reusable. I think that it is. However, even if it's not, this is an important thing because we need to demonstrate that we can bring people back from the moon once they journey there. So this is an important early run. Now, what's a future mission where we actually set foot on the moon going to look like? Well, probably we'll do something with these retrograde orbits in the future where the ship will enter a retrograde orbit and then bring down a smaller test craft that actually lands on the moon and is controlled by the actual astronauts themselves. So stay tuned because we'll see what happens with future missions. But this is a big deal and it's happening tomorrow, so stay tuned. What is this crazy object behind me? This is Io. It's a moon of Jupiter, and it orbits roughly 420,000 kilometers away. The colors that you see are the result of all these volcanic eruptions. You see, it has over 400 active volcanoes that regularly erupt and litter the surface with sulfur and sulfur dioxide. And the eruptions can go as high as 500 kilometers or 300 miles above the surface. What causes all of these volcanoes to exist is frictional forces within the interior. Plates push up against each other just like they do on Earth, causing volcanoes. But the forces are due to tidal forces between Jupiter and its other moons. A lot of people ask me, which interpretation of quantum mechanics do I think is valid? Let me just summarize a couple of them here really quick. There are many others. So there is the Copenhagen interpretation. That's the one accepted by standard physics. And basically what it says is that a particle could be described as a wave function. The wave function has all of the information about the system, from the possible positions that the particle can occupy, to the possible energies that the particle can have, to the possible momentums that the particle can have. And it can exist in a superposition of these until we make a measurement, at which point one of these possible values is actually measured. But then if we leave the system alone, it goes back into this superposition after a certain unspecified amount of time. Now, this is an incomplete interpretation of quantum mechanics, in my opinion, because the length of time specified for how long it takes the system to go back into the superposition is not explained. It's not explained why, when we make a measurement, one of the possible outcomes is chosen. And by the way, the possibility is random. It's like flipping dice. Hence the term, God doesn't play dice. That's why Einstein didn't like this interpretation of quantum mechanics. However, this interpretation of quantum mechanics perfectly explains the behavior of the atoms and the behavior of the electrons. So as far as making predictions for possible values, I think that the theory is perfect at making predictions. As far as explaining what's actually happening, like physically, why is this occurring? There's no explanation given. So that's why it's an incomplete description. Okay, what about many worlds? Many worlds says all the same things as the Copenhagen interpretation, except it goes one step further, and it says when you make a measurement, one of those possibilities is chosen, but there's nothing special about that choice. So all the other possibilities also get chosen in other universes, and everything splits apart into multiple universes every time a choice is made. I doubt this because it doesn't obey any kind of principle of energy conservation. However, as we've seen, energy conservation isn't as strong as we would have thought in classical physics. It can actually be violated in general relativity as well. However, I'm just ultimately skeptical. My end statement is this. I do think that quantum mechanics is incomplete in its description, and I do believe in the future, perhaps the near future, we will actually have a much better understanding of the physical mechanism that lies behind this wave function just choosing a value. And it might still be that it's random, but I think that we will have an explanation in the future at some point as to what's really happening. The Einstein field equations describe all the incredible effects of gravity as the bending of space and time. But there's a huge problem. While these equations work brilliantly and describe a whole host of incredibly experimentally verified effects such as gravitational lensing, black holes, and even dark energy, these equations, which describe the force of gravity as the bending of space and time by energy, have a huge hole in them. And the problem deals with the uncertainty principle. According to the Heisenberg uncertainty principle, the uncertainty in position times the uncertainty in momentum must always be greater than or equal to h bar over 2. This means that the position of an object is never certain, but that means that the gravitational effects caused by matter and energy bending space and time is fuzzy and not well defined because we can't precisely define where an object is. While common sense would dictate that the object is probably located in the vicinity of this uncertainty range, and the uncertainty range is tiny, to be precise, we need to understand how this interaction of gravitational effect caused by the bending of space and time manifests itself in this quantum mechanical uncertainty regime. This is one of the big problems that needs to be solved in order for us to have a unified theory of physics. This is sort of the quantum gravity problem in essence, because we have this uncertainty in position and momentum, but with an uncertainty in position, we have an uncertainty in gravitational bending. So we need to understand, how does this manifest itself, and how do these two different aspects of nature interplay and relate to one another? The biggest lie you'll hear is that entanglement allows faster than the speed of light communication. That's not true. And there are a good number of videos and sources that point this out, but they usually don't explain why, at least not in an easy to understand way. But here's the simplest explanation for why they cannot communicate faster than the speed of light. Let's say we have two observers, Alice on one side and Bob on the other side. Now, they could be separated by a distance of a light year or a couple hundred feet. It doesn't matter. The point is, let's say Alice measures an entangled pair of a particle, like an electron, and let's say she measures it to have spin 1/2. This entangled electron has a partner, like a positron, that has the opposite spin. So when she measures her spin to have 1/2, Bob must measure his particle to have -1/2. That's in the case that the entangled particles came from a spin 0 particle, like a pi meson, that split apart, because spin has to be conserved. So as soon as she measures the spin of the electron, she finds 1/2 and he finds -1/2. He could do the opposite. He could measure his first, and he might find, for his particular case, that his particle has a spin of -1/2, while she finds then that her spin is 1/2. The point is, the spins always have to equal 0, because the entangled angular momentum, the net angular momentum of the system, is 0, and that's conserved. Here's the part that controls whether or not she can do it faster than the speed of light. If she could control her measurement and guarantee that her particle was measured to be -1/2 and control that, then she could decide when to do the measurement, and she could time it, and she could transmit her information faster than the speed of light potentially. But she cannot do that, and he cannot either. If one person makes the measurement first, the other person has no way of knowing that that person made the measurement and that there should be a value associated. If they could control that, then he could know even before he made the measurement what the result was. But since he has no way of talking to Alice when she's separated at some given distance, he has no way of knowing the result of her measurement, and she can't control that result. So she can't say, I will definitely measure the spin to be -1/2 at this time, and I can guarantee that. If she could, then they could communicate faster than the speed of light.